Do Chapter 7. This is acids and bases. We're going to look at the phenomena of acidity. That is, acidity is going to be defined as the concentration of hydronium ion in water. We're going to do some calculations involving the pH scale. Now, the pH scale is a logarithmic scale. It's very important that you have a calculator handy so you can play along. You're going to need to be able to take logarithms and anti-logs. We'll talk about that as we go. Any questions before we get started? All right. It all begins with water. We talked about water in the last chapter. We talked about polar covalent bonds. We said that oxygen and hydrogen have different electronegativities. And because of that, the bonds in water were polarized. Because water has a bent molecular geometry, that's an up and down, that means that the water molecule itself is polar. This has a dipole moment going from the bottom, which is positive, up to the top, which is negative. We see this in the electrostatic potential map. Again, this is a positive region, and this is a negative region. Now, last time in Chapter 6, we talked about the reason that water is able to dissolve ionic compounds. Now, this is not trivial. It really isn't. Ionic compounds are held together electrostatically, and they would really like to just sit next to each other, plus and minus, whatever. Water has the ability to go in and remove ions from this crystal lattice. The way it does it is that the anions in the crystal are solvated by water molecules, and the water dipole is arranged in such a way that the positive ends are all pointed down towards the anion. Likewise, the cation, the positive end of the water pointed towards the cation. This tends to disperse the charge. When you spread out a charge, that makes it more stable. Water is the best molecule in existence that we know of as far as doing this. That's one of the miracles of water. Water also can hydrogen bond with itself. Again, we talked about this last time. We have a hydrogen and an oxygen. These can hydrogen bond. If you look at this calculated map of a cluster of water, the thing that really impresses me is exactly how much one oxygen consumes the adjacent hydrogen. I mean, it really does. It just kind of like eats into its space. This is a hydrogen bond. Now, these are very dynamic. They change 10 to the 6 times per second. Nonetheless, it is very, very powerful in terms of energy, and that's what makes water, again, such a unique solvent. Well, in addition to the fact that they can hydrogen bond and basically consume half of the sphere of the adjacent hydrogen, water has the ability to undergo what's known as AUTOPROTOLYSIS. That is, if you put two waters next to each other and you let them hydrogen bond, sometimes this bond becomes so compelling that the hydrogen on one water is actually physically transferred to the other water. process looks something like this. And when that happens, you form a hydronium cation, that's H3O+, and you form one hydroxide anion, OH-. Now this is kind of an amazing process. If you think about it, what we're doing here is literally breaking a covalent bond. We're breaking the covalent bond and transferring the hydrogen atom from one oxygen to another. I can do this again by clicking my button. There we go. We have hydronium and we have hydroxide. Now, one of the key things that you need to know, one of the key things you need to understand is that anytime you have pure water at 25 degrees centigrade, that's room temperature right here, right now, this is going to happen over and over again. This is going to go up and go down very, very quickly. And at any moment, at any second, the concentration of hydronium and hydroxide are equal, and they're both equal to exactly 1 × 10⁻⁷ moles per liter. This is a number you want to remember. 1 × 10⁻⁷ molar in pure water, hydronium and hydroxide. They're both exactly the same. We'll see that this is where pH 7 comes from. Everyone has heard of that. pH 7, that's neutrality. In neutral water, we have 10⁻⁷ molar hydronium and hydroxide simply because we autoprotolysis to form the plus and the minus. Any question on the concept? Well, you know, when we do this, we're going from neutral water, which is neutral. Nature loves neutral. And we're making ions that have real charges to them. And frankly, nature abhors a charge. It really likes neutral. If we look at the electrostatic potential map for hydronium and hydroxide, you know, they're huge. This blue is positive, remember, red is negative. These are a huge set of point charges. So the question that you should be asking is, why in the world does this happen? Really, why does this happen? Again, it has to do with the property of water. Let's look at hydronium itself. This is H3O+, and this is its electrostatic potential map. The oxygen at the top here, a little bit of green, but big, big blue bottom. You can see it better on this angle. Big blue bottom, a little bit of green on top of the oxygen. That means we have a huge positive charge down here. And how does water get away with going from neutral to this very positive sort of thingy? Tell them hello for me. So how does this really happen? The reason it happens, once again, is water itself. If we take the hydronium ion and we place it somewhere like this, this is H3O+, what I want to do is to place only 3 waters around it, just 3. Remember, each of these hydrogens can do hydrogen bonding. So let's put 3 waters around, and we're going to let this bond here, this bond here, this bond here. Water is so good at dispersing a charge that if you take this whole cluster, feed it to your computer, and do an electrostatic potential map, again, this is what it looks like before we start. What it looks like is something like this. We not only have lost all the blue here, but my goodness, here where the oxygen is, it's not just barely green, but it's yellow. This is the amazing property of water to disperse the charge over its neighbors. Now, water doesn't exist as 3 things around one central. It actually exists largely as groups of about 8. Now, they're very dynamic. Again, they change 10 to the 7th, 10 to the 8th times per second. But, nonetheless, a hydronium would typically be surrounded by a group of waters like this. Now, here's our H3O+. Again, it looks something like this. Big blue bottom, slight green top. If we take this entire cluster, feed it to our computer, and ask what the potential map looks like, we get something like this. Not only is the green cap gone, but now it's red. And we have no hint of blue anywhere. Over these 8 waters in this cluster, we have dispersed totally all of this charge. This is the amazing property of water, to be able to take a charged particle, hydronium in this case, and disperse the charge everywhere. All right, so much for raving about water. What does this have to do with acids and bases? Well, water is so good at dispersing this charge that it not only works with water itself, but it works with many, many compounds that have polar covalent bonds. We looked at hydrogen fluoride, HF. Chapter 6. We said that because of the difference in electronegativity, fluorine is the most electronegative atom. It sucks the electrons towards itself, leaving the poor hydrogen down here very electron deficient. If we take something like HF with a real covalent bond between it, we see exactly the same thing that we saw in water itself. That is, HF, here's the water, and they're hydrogen bonded, right? What can happen is this hydrogen can be transferred from the HF to the water. Now remember, this involves breaking the covalent bond. We're breaking a bond. And we're going to transfer this hydrogen to the water. When we do that, we wind up with hydronium, H3O+, and the fluoride anion. This is what we refer to as an acid in solution. Anything that dissolves in water, water is able to break the covalent bond and form hydronium ion. That is an acid. Now we would show this way. HF plus water gives hydronium, that's this, and F minus. That is the process of generating something that is acidic. If it's acidic, you make H3O plus. Any questions? All right, now when we did water, we noted that these two were sitting next to each other still, weren't they? So once you hand it off this way, you can hand it back the other way. So we can not only go this way, that is, make the ions, we can go backwards and make the neutral HF. In chemistry, this is something we call an equilibrium. We have two reactions, one going forward, one going backward. They go at the same time. The rates will be different. In this case, if the rate this way is faster, you'd have more H3O plus. If the rate this way was faster, you would have more undissociated HF. But it's called an equilibrium. An equilibrium is shown in chemistry using a double arrow. Now, this is not a double-headed arrow. Make sure you know that. That's different. You won't see that in this course, but you would see it later. Double-headed arrow refers to resonance, but this is one arrow on top of the other. And it simply tells you that this reaction goes back and forth and back and forth and back and forth. Once again, 10 to the 6th, 10 to the 7th times per second. Very, very fast. This is an equilibrium. Any questions? When we look at this equation, we have to call it something. We don't want to call it, George. We're going to call it the equilibrium dissociation. In this equation, we have the undissociated acid, HF, and we have the dissociated acid, hydronium and fluoride. We will see that there are two classes of acids we're going to deal with. And it has to do with this equilibrium. Bottom line is really pretty simple. If we have lots and lots of hydronium, it's called a strong acid. H3O plus is the acidic form in water that we call an acid. If we have mostly undissociated acid and just a little bit of this stuff, it's called a weak acid. We have two categories, strong acids all the way on this side, lots and lots of H3O. Weak acids, very little H3O, lots of stuff on this side. It's a simple equilibrium dynamic. Now in this course, we're only going to deal with strong acids. Strong acids, once again, you put them in water, you break the covalent bond, and you make hydronium. Now, no one believes me when I say things, therefore we will listen to this woman. Oh, before I say that, Bronsted acid-base theory. Make sure you understand the terminology. Bronsted acid is a proton donor. So HF donates the proton. Bronsted base, water in this case, accepts the proton. Proton donor, acid, proton acceptor, base. All right, let's listen to our woman.
A strong electrolyte that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Well, I'm sorry for the difficulty with the thingy here. I have no idea why it did that. That wasn't nice. I might even try that again.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
Hydrogen chloride is an example of a strong acid. When it hits water, it virtually 100% ionizes to hydronium and chloride. Now, this shows only hydronium and chloride. That's not right. For every billion H plus Cl minuses, you'll have one HCl. But it's pretty much darn near all the way this way. That's what an equilibrium means. You have lots and lots of this, and just a tiny bit of this stuff. Now we've used hydrochloric acid in the lab. These are our common strong acids. HCl will ionize in water virtually 100%, so 99.999% in water will be hydronium and chloride. One tiny molecule sitting around with HCl. Nitric acid, we haven't used this guy for a couple reasons. Concentrated nitric acid is really bad stuff. If you get some on your skin, it turns it brown immediately, gives you bad burns. This was used as a concentrated nitric acid, was used as a rocket fuel in the Scud missiles. You know, way back, remember, Scud missiles. And the problem with shooting down the Scud missile in flight was that you released all this concentrated nitric acid. So yeah, it didn't blow up, but everybody got doused with this cloud of concentrated nitric acid, which is bad stuff. If you think about it, this is just nitrate with a hydrogen on one of the oxygens. That's nitric acid. Very strong acid, very corrosive. Perchloric is even stronger, actually. This is perchloric acid, so ClO4 is chlorate. Put a hydrogen on one of the oxygens. Very, very strong acid. Now these are all referred to as monoprotic acids. Monoprotic means we have one proton to donate. When we talk about proton donation here, the hydrogen that comes across is donated without electrons. So if you have a hydrogen atom with no electrons, what is it? It's a proton. Monoprotic acid. Sulfuric acid, everybody's favorite acid. This is sulfate with a hydrogen on two of the oxygens. We can take the first one off and form hydrogen sulfate. We can take the second one off and form sulfate. So as opposed to a monoprotic acid, this is diprotic. Two hydrogens we can lose. The only triprotic that we would hit in this course would be phosphate. So H3PO4, we have a triprotic acid. Any question? Now there's a concept here involving acids and their proton acceptors. In this case, HCl is the acid, and the proton acceptor is water. So we transfer it to make hydronium, and we're left with chloride. In the Bronsted acid-base theory, this is referred to as a conjugate acid and a conjugate base. Simple thing to remember, the acid donates the proton, the base accepts it. That's all you have to remember. Acid donates, base accepts it. In this case, we're donating a proton from nitric acid. Who's accepting it? Water. Water is accepting the proton. Once we lose the proton here, we form the conjugate base, which is nitrate. So you take your acid, remove the hydrogen, and you make the conjugate base. Let's look at some examples. Remember that the conjugate base will have one less proton and one more negative charge. Now this is important because a very simple test question, exam question, has to do with acid-base pairs. Just remember, the acid will have one more proton than the base, and will have one more negative charge on this side than the other. That's because the proton is positive, right? If we lose a proton, we must have a negative charge. So let's look at an example. Here are some standard strong acids. In this, HCl is clearly our acid. So if we were asked to label the conjugate acid, it would be this. Step 2, what is formed after you lose the proton? We're going to lose the proton here. We're going to form Cl- with a negative charge. This would be the acid, and this is its conjugate base. They differ by one hydrogen and one negative charge. Any question? Simple concept. They differ by one hydrogen and one negative charge. Sulfuric acid, we can do it twice with sulfuric acid, can't we? If sulfuric acid loses a proton, it would be the acid form, right? If it loses one proton that gains a negative charge, what is it? Hydrogen sulfide. This is the acid, and this is the conjugate base. We lose a hydrogen, and we gain a negative charge. Once we make hydrogen sulfate, it's diprotic, so we can do it twice. The acid in this case is going to be hydrogen sulfate. It's going to lose a proton and a negative charge. If we lose the hydrogen, we make sulfate, gain one more negative charge, we have sulfate anion. This is the conjugate acid, and this is the conjugate base. Now this last one, instead of using water, I'm using ammonia. Remember that there is speculation that liquid ammonia can support life, just like water can here on Earth. So further out in our solar system, we have oceans of liquid ammonia, and they support life. Well, one of the things you have to do to support life is to support ionization. So in this case, we're dealing with nitric acid as the acid. We're going to lose a proton and form nitrate. So conjugate acid pair would be this. Now, because we're not dealing with water, I think it's interesting to deal about the reverse reaction. So this goes backwards this way, right? In the reverse direction, who is the acid? Well, ammonium is going to donate the proton to nitrate, going this way. So this is the acid, and that means that the corresponding base is this. So think about these as an equilibrium. They go back and forth and back and forth and back and forth. You can do it forward and reverse. Now, there's a tutorial that describes this. Tutorial basically deals with aqueous solutions, so just waters. This is one of the tutorials that earns you 5 points, so let's pay attention. Conjugate acid-base pairs. What you do in these guys is you type in something into these fields. Now you can't do super subs, so you just type it in straight and it'll figure out what you're trying to say. What we're doing here is we're looking for the acid and the base that can react to give F- and hydronium. So think about it. Let's do our first one. The conjugate acid of F-. Remember, a conjugate acid has one more proton, doesn't it? And one less negative charge. So all you have to do here is take your F- and put a proton on it. Secondly, we have hydronium on this side. The question is, what's the conjugate base? What gains a proton to form hydronium?
H2.
That's right. That is just simply water. So look at the equation. We donate the proton to water, get F- and hydronium. Let's do another. Going this way, we have chlorate anion, NH3O+. All right, if chlorate anion accepts a proton, what's it going to form? HClO3. Right, just that plus one more proton.
H2.
ClO3 gains a proton, you get HClO3. On this half, hydronium is donating its proton. Once it donates it, what do you get?
H2.
That's right, just plain old water. Hydronium donates proton to chlorate, HClO3. Water loses its proton, so it's simply water. Do one more and I'll hush. we have hydrogen sulfate anion and H3O plus. Who's going to be the acid here? H3O plus is always the acid. Remember that. H3O is always the acid. So it's going to donate a proton here. If we put one more proton on HSO3 minus, we would get H2SO3, sulfurous acid. After hydronium loses its proton, what are we left with? Right, just plain old water. And that's it. Now, once again, this is a tutorial. Do it. Get 5 right, submit it, you get your credit. I have some examples of exam questions. Now, exam questions about this have to do with who's the acid, who's the base, and stuff like that. Before we do that, however, I'm sorry, I just looked at the slides. Before we do that, let's deal with the other concept, and that is the strong base. Now, we've talked about sodium hydroxide. Hydroxide, we remember, is a polyatomic ion with a negative charge, OH minus. Whenever you take something like sodium hydroxide, this is lye. Anyone ever used oven cleaner? Okay, I have too. This is basically sodium hydroxide. Very, very strong base, great for cleaning, bad for your hands. Sodium hydroxide ionizes totally in solution to form sodium and hydroxide. Now, if you happen to have a strong base in the presence of a strong acid, what happens is the base will react with the acid and it will form water. So you start off with a solution here that's very, very basic, very alkaline, caustic, nasty stuff. You have another solution here that's very acidic. Again, nasty stuff. You put them together in the same amount, they mix. What do they form? Water. This is called neutralization. Here is my video example of neutralization. If I take hydrogen chloride in water, I'm going to form hydronium and chloride ions. We know that because it's a strong acid. It all breaks apart. Hydronium and chloride. In this pot, I have sodium hydroxide, sodium and OH minus. Again, they're in water, totally dissociated. If I take an equal amount of both of these and put them together, what's going to happen? Well, the hydroxide is going to react with hydronium to pull off this hydrogen. Sodium's going to go along for the ride. And it should look something like this. We pull off the proton, we make water, and what are we left with? Sodium and chloride. HCl, sodium hydroxide, sodium chloride, and water. This is a neutral solution now. We started off with two solutions that were very different. This is very acidic. This is very basic. We mix them together. The OH minus will react with hydronium. We get water, and we're just left with sodium chloride in solution. Strong acid and strong base simply gives a salt. Any questions? All right, well, we just made a solution of water by taking a strong acid and a strong base. But we know that if water sits there by itself, it will spontaneously generate hydronium and hydroxide. But these are always in exactly equal concentrations. And that concentration is always 10 to the minus 7 molar. Neutral water will have 10 to the minus 7 molar hydronium and 10 to the minus 7 hydroxide. Let's look at what's called a titration problem, a neutralization problem. Remember we talked about the concept of molarity back in chapter 5. We have in this experiment 125 mils, 0.025 molar solution. That means there are 0.025 moles per liter. We're going to react this with 125 mils of hydrochloric acid solution, and we want to know the molarity of our hydrochloric acid solution. This is an experiment that you will do in general chemistry, where you take an unknown and a known and simply do it to neutrality. Here's our equation. 1 mole of sodium hydroxide, 1 mole of HCl. So the number of moles here has to be equal. On this side, we know that we have 125 mils of 0.025 molar sodium hydroxide, and we're going to add 125 mils of hydrochloric acid. We wind up with a neutral solution. So what's our concentration here? The thing to remember, you know, every night when you go to sleep, what do you say? PV equals nRT. Remember that. PV equals nRT, the gas law, right? Well, here's another one. Concentration, molarity, times volume in liters gives moles. So here we have a concentration and a volume in moles, and this is going to give us moles of base. Concentration times volume equals moles. Here our liters cancel. We're only left with moles as our answer. And that's about 3 times 10 to the minus 3 moles. So that's how many moles of sodium hydroxide we have. Now, according to our equation, 1 mole of HCl reacts with 1 mole of sodium hydroxide. So here's our moles of sodium hydroxide. Here's our volume, that's molar. Moles of sodium hydroxide is equal to moles of HCl. So what's our concentration? Do our division. It's the same thing, 0.025 molar. Concentration times volume gives us moles. Just like PV equals nRT, except it doesn't rhyme. Any questions?
That question, the -10 to the -3.
That's -2.
Huh?
10 to the -2.
No, you got 10 to the -3.
10 to the -3 moles, but you divide it by 0.1.
Right, but where do we get the 10 to the -3? How do we come with that?
Take your magic calculator, feed it to it. It should be 10 to the -2.
Magic calculator.
I hope. You know, sometimes I make mistakes on slides just to see if people are paying attention. That's the only reason.
Quick question, Dr. Young.
Yeah,
So it's not moles per liter, because you have the liter on the bottom? or
this
just-
is molarity, so that's moles per liter,
Oh,
right? Mole per liter is molarity, right?
okay.
Good catch, though. All right, exam questions. I promised these were coming. These are actual archive exam questions. In which of these pairs is the acid followed by the conjugate base? Real exam question. Now remember, what happens to an acid? Only thing that happens to an acid is that it loses its proton and gains a negative charge. That's the only thing that happens. Has to be the same compound on both sides. They differ by a proton and a negative charge. Acid loses the proton to form its base. All right, our first set here. H plus HCl. No, you really can't lose a proton from H plus, can you?
No.
No, that doesn't work. NH3, if we lost a proton here, what would we get? NH2 minus. That doesn't work. Lose a proton from here. HPO4, 2 minus, we would get we would get only phosphate, PO4, 3 minus. Lose a proton. Hydrogen carbonate, we lose a proton, what do we form? Carbonate. Right? Carbonate. CO3, 2 minus. Here we have gained a proton. Clearly this is our correct answer. I can guarantee that you will see a question similar to this on your next exam.
Okay, so you said.
All right, here we have a whole equation. What's true? Hydrogen carbonate's the acid, water's the conjugate base. Hydrogen carbonate's an acid, carbonate's the base, blah, 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 blah. Remember, once again, what happens to an acid? It simply loses a proton, nothing else. It loses its proton and gains a negative charge.
Number E is the answer, I think.
So which of these does the acid lose a proton to form the same compound minus a hydrogen but with 1 negative charge?
That would be
Well, it's not this, is it? Because these are different compounds. Not this, not this, not that. The only one that has the same compound
Is C?
is B.
B?
We lose a proton, add a negative charge to form carbonate. It's the only one. Has to be the same compound.
I see it now.
Conjugate acid of hydrogen sulfate is what? Now think about it. If this is the base, how does the base differ? The base has one less proton and one less negative charge, right? The base is going to gain a proton, lose a negative charge to form the acid. So what works? If we put a proton on here and lose a negative charge, you get everyone's favorite acid, sulfuric acid. Gain a proton, lose a negative charge. All right, any questions on that? Let's go back and deal with what we said earlier about a neutral solution. So if I had a bottle of water up here, so I didn't get worse while I'm talking, and I don't. But if I had a bottle of water, let's say pretend it was pure 100% water. That water would have hydronium and hydroxide, both at exactly 10 to the minus 7 molar. 10 to the minus 7 molar. That's what we mean by a neutral solution. Water always has hydronium and hydroxide, and it's always 10 to the minus 7 molar. Now this is room temperature. That's a neutral solution. Now this isn't always the case. Sometimes we have solutions where we have more hydronium than hydroxide, more hydroxide than hydronium. We're going to describe a solution that has more hydronium. Remember, hydronium was the acid stuff, right? If you have more hydronium, that's called an acid. If we have more hydroxide, it's called a base. If they're equal, if they're both 10 to the minus 7, that's neutral. All right, in order to deal, now these are very small numbers. 10 to the minus 7. If you had to sit there with your calculator and do this, it would be a chore. So back in the days, way before calculators were invented, chemists decided that there was a neat way to get around this, and that was to use a logarithm. The logarithm, base 10, is simply the exponent. So if we had 10 to the minus 7, the exponent would be minus 7. But chemists are very positive people and don't like negative exponents. So instead of having it 10 to the minus 7, they put a minus sign in front and called it 10 to the 7th. So in neutral water, plain old, absolutely pure water, how much hydronium do we have? The minus log of 10 to the minus 7 is 7. That is called pH 7. 10 to the minus 7, change the sign, 7. That means neutrality. Now, this is a log scale. Again, we're putting a minus sign in front. Think about the log scale. If we have 10 times 10, that's 10 squared, right? The logarithm of that is 2. Feed that to your calculator. If you don't have it on, turn it on. Warm it up. Make sure you can do log of 100 and get 2. If we had 10 times 10 times 10, that's 10 to the third. The log of 10 to the third is 3. So all we're doing here is talking about this exponent. That's all in the world the logarithm is. Now sometimes it's not an even number. Sometimes the log might be 2.5. But your calculator will tell you that. And we'll see examples of that. So again, feed this to your calculator. Make sure that you get it. 10 squared is the same as 2. The way you do it is you would type in 10 to the x, put in 2 for the x, you should get 100. Any questions? Also, you type in 100, hit the log button, you should get 2. Now, I told you from the very first day of the course, you need to have a calculator and you need to love it, right? Because this is going to be your friend on exams and quizzes. Make sure, everybody's calculator is different. Make sure you know how to type in 100, hit the log button and get 2, or type in 10 to the x, put in 2, and get 100. Those are your 2 important operations. Any question? All right, let's go ahead and move on. Oh, here we go. 10 to the 2.5. 316. Try this on your calculator. Type in 316 and hit log. You should get about 2.5. Yeah, close. Close.
Are we rounding?
Yeah, you round it.
Oh, okay.
You know, back in the old days, and I lived through it, we didn't have calculators, right? And so there was something called log tables. Slide rules, same thing. And you would have to look it up on a log table, big table in the back of the book, and figure out what the log of 316 was. So, you know, it's a real, calculators have just made it so much easier. But make sure you know how to use it. Any question? All right, well, let's go back to water. pH is defined as the negative log of hydronium. Sometimes it's just written as H+, same thing. Now in neutral water, how much hydronium do we have? We have 10 to the minus 7 molar. Don't ever forget that number. 10 to the minus 7 molar. So, the negative log of 10 to the minus 7 is what? It's going to be 7. You take the exponent, you change the sign. That's all there is to it. Take the exponent and change the sign. This is where pH 7 comes from. Whenever you see something that says it's pH 7, that's telling you it is 10 to the minus 7 molar hydronium. It also has 10 to the minus 7 hydroxide, because they have to be equal. Any questions? pH of pure water is 7. Now remember, we're changing the sign here. So if we have lots and lots of hydronium, the hydronium is going to be less than 10 to the minus 7, which makes it a small number. Like if our hydronium was 10 to the minus 3, the pH would be 3. Anytime you have a pH of less than 7, that's an acid. Conversely, anytime you have a pH that's greater than 7, that's a base. Less than 7, acidic. More than 7, basic. Yeah, you can figure this out. Less than 7 is acid. More than 7, basic. Yeah, dude. I promise you.
It's alkaline.
Now, just like we can have something called a hydronium, the pH scale, we can also have something called a pOH scale. Now, I always thought this was a little bit cruel to throw on people, but it's the same concept. If you simply take hydroxide, take its negative log, you get something called the pOH. So let's pretend we're dealing with pure water, right? Hydronium is 10 to the minus 7, so its pH is 7. Hydroxide is also 10 to the minus 7, so the pOH is also 7. Now, hydronium and hydroxide multiplied together are always 10 to the minus 14. 10 to the minus 7, 10 to the minus 7, 10 to the minus 14. This gives us an important relationship, something you never want to forget. Under all conditions, pH plus pOH will always equal 14. Remember that. Write it down, put it on the back of your palm. Because hydronium is 10 to the minus 7, hydroxide is 10 to the minus 7. Multiply them together, you get 10 to the minus 14. Change the sign. These two together will always equal 14. This is a really useful number. pH plus pOH always equal 14. Likewise, if we have a real concentration for both, they will also always equal 10 to the minus 14. Now, depending upon the problem you're dealing with, you might be given a hydronium. Calculate this, but you know this is a constant, so you can easily calculate OH minus. If you're given a pH, you know that the pH minus 14 is always OH minus. Always the POH. Now this is actually really simple and fairly useful. Any questions before I click my button? All right. The product, hydronium times hydroxide, is always 10 to the minus 14. If we know one of these, we can calculate the other. It's always going to be 10 to the minus 14. These two multiplied together are always this. So if I told you hydroxide was 5 times 10 to the minus 8 molar, what's the hydronium? Well, you would sit there for a moment and you say, I don't know. But then it would dawn on you. Hydronium times hydroxide is 10 to the minus 14. If I know hydroxide and I know this, I can calculate hydronium anytime I want. Here we have 10 to the minus 14 divided by our hydroxide. Do our simple math. 1.98 times 10 to the minus 7. You see why you love your calculator? If you're given one, you can always calculate the other. Now this is going to be important to you because we're going to do a tutorial where you'll be given one and you have to calculate the other. So make sure you understand this concept. The two multiplied together are always 10 to the minus 14. I hope you get me in that picture too. Any questions? All right.
You know, I'm confused. I am.
This times this is always 10 to the minus 14.
Right, but I'm talking about down at the, okay, at the HO negative is 5.
So what here we have 10 to the minus 14, that's this,
Right.
divided by hydroxide, which we were given. Divide it, feed it to your calculator, you should get 2 times 10 to the minus 7.
Oh, that's what it's going to give me. Okay, let me see.
All right, before we actually get into doing these calculations, let's just take a breath and let's talk about the pH scale in general. What does pH mean in real life? Well, in your stomach right now, it's probably about 1.5. Depending upon how stressed you are, it could be a little bit less, a little more acid. Very seldom gets above that. But stomach acid at 1.5, think about that, pH 1.5. That's really strong acid. Isn't it amazing that your stomach doesn't just dissolve itself? It actually is. If we have 1 molar HCl, that's stronger than we've used in lab, the pH is 0. Going back up the scale here, really bad wine is about pH 3. I'm sure we've all tasted that. Bad coffee is about 5. We hit 7. Remember, 7 is neutral. blood, sweat, and tears, slightly on the alkaline side, about 7.2, 7.4. So in here somewhere. Seawater is a little more, about 8. Bleach. I'm sure everyone's used bleach, sodium hypochlorite. It's about a little over 12. Really, really strong. And up here with 1 molar hydroxide, we're at 14. The scale can actually go above 14 and below 0. So if we have a really, really strong acid, we can have a pH of -5. Really strong base, we can go -15, -16. But this is the scale that we typically deal with. Now, how do we measure this? In a perfect world where we had all the lab equipment in the world you could break, we would use a pH meter. A pH meter has this little tiny probe. Probe itself isn't tiny, but it has a microscopically thin glass membrane. When you put it in solution, it sets up a potential across this membrane. The potential is read by a millivoltmeter, and that's interpreted in terms of the pH. The real problem here is this microscopic glass membrane breaks. Why? Because it's microscopic. Why else? Because you're really clumsy. The problem is they cost $100 to $200 each. So you go and you shove it in your little beaker, break it, a couple $100 down the drain. So you're probably not going to use a classic pH meter at this level. Instead, you'll probably use something like this, which is pH paper. Now, pH paper is an engineering marvel. It has compounds embedded in the paper that change color depending upon the pH of the solution. This is a very carefully defined mix. In this particular thing, it turns red if it's acidic, and up here we're at like black-purple if it's basic. You can take and you can go through the whole spectrum here. It's just amazing the way they've managed to put this together. This all has to do with indicators. Indicators are organic compounds that can gain or lose protons depending upon pH. Not only that, but when they gain or lose a proton, they change color. Phenolphthalein, that's this guy. This is the one that we will actually use in lab. Down in acidic solution, we have protons of both of these OH groups, and it's colorless. When we hit pH 8 or 9, we start losing a proton here, and it turns pinkish to purple. This is the classic general chemistry indicator. If it's colorless, it means you're acidic. If it's pink or purple, it means it's basic. You see that some of these are really interesting. Thymol blue goes from red to yellow to green to blue. Methyl orange from red to yellow. And we have yellow, green, blue, etc., etc. Now you might sit back and think that, my goodness, chemists are so clever. They are just so clever. And you're right. But red cabbage beat us to it. If anybody here cooks, and I hope you do, and you cook cabbage, which you should, I hope you realize that how you saute your cabbage makes a real difference. Because cabbage juice, red cabbage juice, is a natural indicator. If you take a cabbage and you smoosh it up with the juice and you make it acidic, you get this brilliant red color. As you move towards neutrality, you hit the purple that matches that. Slightly alkaline, you go blue. When you get fairly alkaline, you get this disgusting green. So if you cook cabbage and you want it to look nice, the trick is make sure that it hits slightly on the acidic side of neutrality. That means a little bit of vinegar. If you were to take your sauteed cabbage and add a little bit of baking soda, so it was alkaline, it would turn this disgusting green and nobody could eat it. Little bit of vinegar and you get beautiful purple red cabbage. So cabbage thought of this long before we did. Any questions? All right, let's look at an example of how we do this in lab. What we're going to do is take a solution. There's something in here, and there's something in here. This is going to be an acid and a base. We have phenolphthalein in here, so it is colorless, clear. Up here we have a base. And what's called a titration, you start off by adding little bits of base to acid, and you're looking for a color change. When we have 1 mole of acid and 1 mole of base, it'll be neutral, won't it? When we have 1 extra drop of base, this will turn pink. That's how you know you hit neutrality. So what we're going to do is start off with some volume in this pipette. Going to open this very, very, very carefully. Going to dribble in bit by bit until we get our color change. We look at where we started, where we ended, we know how much base we added. So we know the concentration of this base, we know its volume. What do we remember? Concentration times volume is moles. So we know how many moles of base we added. We know what volume we had down here. Therefore, we can calculate our concentration. Now, we're not actually going to do that problem here. This is more a general chemistry calculation. But when you hit general chemistry, and I hope you do, and then organic, so we can see each other again. When you hit general chemistry, you will use a burette like this. You will then calculate the concentration of your unknown acid. You can do that because volume times concentration is moles. All right, let's go one step further now. Pull out your calculator, I'm pulling up mine. I have a solution. I'm allowed to use a pH meter because I won't break it. And I find that the pH of the solution is 7.23. What is my hydronium ion concentration? How in the world do you do this? But we have to remember that the pH is simply the negative log of hydronium, isn't it? That's the definition. If we know the hydronium ion concentration, we take its log, change its sign, and that gives us pH. That's all you have to do. Now let's go ahead and just get rid of our -1, again, because we're positive people. So 10 to the minus pH will give us hydronium. Now is where you look at your calculator and you say, what the heck? You're looking for the button that says 10 to the x. 10 to the x. Everybody's calculator is different. Mine looks like this. I'm going to type in minus 7.23. And then I'm going to look all over my screen here until I see this little thing here in green that says 10 to the x. To get to the green, I have to push this button and then this one. And when I do that, by George, I get 5.8888 times 10 to the minus 8. Now feed that to your calculator and make sure it comes out the same, or at least close. Once again, type in minus 7.23, hit 10 to the x. And you should get something like that. This is our hydronium ion concentration. Any question? All right, as if this isn't confusing enough, I'll stick in one thing that probably everyone that ever will teach you chemistry won't know, but you're going to know it. And that is that this is the wrong answer. Now, why is this the wrong answer? It's a technicality. We have 7.23 as our pH, right? Again, nobody else knows this except you and me. But 7.23. A pH or a log value is made up of two parts, called the characteristic and the mantissa. Characteristic is the number in front. That's your power of 10. The mantissa describes how many significant figures you have in your number. So we have two. This is our characteristic. This is our mantissa. So we have two significant figures. So we would have to round this to 5.9. Once again, nobody else in the world knows this except us. Don't tell anybody. But when you're dealing with logarithms, and this would never be on an exam, okay? Don't worry about that. This would never be on an exam, but you know something that nobody else knows. Any questions? Remember, 10 to the minus pH. Put in your pH as a negative sign, 10 to the x, and you should get something pretty much like that. Now I hope you guys all have working calculators. Let's go ahead and do a couple. If our pH is 4, what's our You can fire up your calculator, right? Or you could remember that the pH is simply the negative log of hydronium. What's the negative log of 10 to the minus 4? Up to 10 to the 4? 10 to the minus 4. So for an even number, it's really easy. All you do is change the sign. If our number here was 12 as our pH, that would simply say that the hydronium was 10 to the minus 12. This solution is acidic. This solution is basic. Now, nobody is ever going to ask you for an even number. Maybe I would, but nobody else would. So these guys you're going to have to enter into your calculator. You want to enter minus 5.5 and hit 10 to the x. Minus 5.5, 10 to the x. You should get something 3.2 times 10 to the minus 6. Now with most phones come with a calculator. Most phone calculators don't do exponents easily. So you have to kind of yell at them to get them to do it. Or download a different app or something like that. A simple scientific calculator, you can pretty much toggle between decimal and scientific and get numbers like this. For the exam and for the tutorial, make sure you can do this. Here we would enter minus 1.32. We would hit 10 to the x, and with any luck, you should get 4.8 times 10 to the minus 2. Yeah. Sorry, I didn't quite hear your distress. And our last one here, we have 7 with lots and lots of decimal points afterwards. Number one question, is this solution acidic or basic? It's basic, right, because it's more than 7. So you would type in minus 7.02 whatever, hit 10 to the x, and you should get something like that. Any questions? For this one here, you would type in 7.025 whatever, minus 7.02. No, you get your phone number. Let me try. So let's put it on. What's our number? That's why I hate using somebody else's calculator. You have to use the thingy to figure out what we're doing. Okay, but that's the answer. Just sit and practice it all night. Sit and practice, you'll get it. Again, you use your calculator. Yep. All right, let's do this backwards. Let's pretend we have a hydronium ion and we want a pH. Now we can do this because we know hydronium, this is our number, and the negative log of that hydronium is pH. So this one's actually much easier. Here you need to take your calculator. I'm going to type in 7.04 times 10 to the minus 7. So you have to know how to enter exponents. On my calculator, what is it? Oh, here it is. 7.042 times 10 to the minus 7. So figure out how to type that into your calculator. Now, this has to be a negative sign. So you have to find the plus minus button somewhere and change it to a negative. When you do, take its log, you should get this. Negative log of this guy is something like this. Here we have three significant figures, so I wrote round this to 152. Again, nobody knows this except you and me. Let's go backwards here. Type in 7.042 times 10 to the minus 7. Type that in. Hit your log button. Just hit the log button, that's all. Everybody has a log button somewhere. When you do, you should get about minus 6.15. Got it? All right, see? I knew we'd figure this out.
Right, but this is kind of backwards one.
And then you have to simply change a sign to make it positive. Now you know you paid so much for these calculators. Isn't it fun to finally use it for something? Of course it is. Let's go ahead and do a set. PA, or hydronium, of 1 times 10 to the minus 4. Even without looking at your calculator. What is that? That's right. The negative log here is going to be 4. So even without touching your calculator, this is 4. Now these guys aren't quite so simple. You need to type in 5 times 10 to the minus 4, hit log, change the sign. Type in 5 times 10 to the minus 4, hit log, change the sign. You should get about 3.3. Our next guy, 1.37 times 10 to the minus 8. You type that in. Hit the log button. Change the sign. you should get about 7.86. Now, a very standard question that I'll put on the final exam, if everyone's paying attention, is I will give this solution here, 7 times 10 to the minus 7, and ask if it's acidic, basic, or neutral, or none of the above. Okay? There are so many 7s in here, everybody always says it's neutral. But of course it's not. There is more hydroxide than there is hydronium.
So
If it was neutral, it would be 1 times 10 to the minus 7. So what is this exactly? What's the hydronium here? Type in 7 times 10 to the minus 7. You should get 6.15. Very standard trick question. 4.6 times 10 to the minus 5. Type it in, hit log. Change the sign. You should get about 4.3, 4.4. Now, of course, there's a tutorial for this, right? There are a couple. Basic pH relationships. I think it might be called pH 1. Could be called pH 2, I don't remember. But it's one of those. What is the pH if OH minus is 6 times 10 to the minus 11? Now, in order to do this, you need to figure out hydronium, don't you? How in the world do you do that? Well, you remember that hydronium times hydroxide is 10 to the minus 14, right? You remember that. So, 10 to the minus 14 divided by hydroxide is going to give us H+. Once you get hydronium, what do? Take its negative log, and that's your pH. So for our first step here, 10 to the minus 14 divided by our hydroxide gives us 1.6 times 10 to the minus 4. Quickly type in your calculator, 1.6 times 10 to the minus 4, hit log, change the sign, and with any luck, you should get about 3.79. With any luck. One more from this one. Oh, this is simple. What's the pOH if the hydronium is this guy? What do we remember about pH and pOH? They always add up to what? 14. They always add up to 14. So all we have to do is convert hydronium into pH. And we know that pH plus pOH must be 14. So this is hydronium. Type it in. It is log. Change the sign. And what do you get? Well, I did it differently, didn't I? Shoot. I didn't remember. I did it the hard way. I said in this one, here we have hydroxide, or here we have hydronium. 10 to the minus 14 divided by hydronium is hydroxide. Going to take its negative log. Well, the hydroxide turned out to be 3.53 times 10 to the minus 12. Type that in, hit log, change the sign, what do you get? With any luck, you'll get about 11 and a half. Now, clearly, there are two ways you could have done this problem, right? You could have figured out the pH, subtracted from 14, and got the POH. But we're going to do that in just a second. And this is the tutorial called pH2, or something like that. In this guy, you have a table. And in this table, you'll be given one thing. And in order to get it right, you have to fill in the rest. Now, in this one, we're given a pH. Right away, we know what the POH is, don't we? Because they must add up to 14. We know that. They must add up to 14. If we know a pH, we can take 10 to the minus pH and get hydronium. We can then divide that by 10 to the minus 14 and get hydroxide, and simply, POH is trivial. So, for POH, 14 minus pH, that's this guy. Simply subtract them, what do you get? A little over 3. Here we have a pH, 10 to the minus pH. Feed that to your calculator, type in the number, change the sign, get 10 to the x, so 10 to the minus 10.83. You should get about 1.5 times 10 to the minus 11. For OH, we can simply take the POH value here, do 10 to the minus POH, that's this thing. So you type in 3.17, change the sign, hit 10 to the x. You should get about 6.7 times 10 to the minus 4. So this tutorial lets you do it all. Let's do one more of these. If I give you hydronium, calculate hydroxide, pH, and POH. How do we do that? We know that 10 to the minus 14 divided by hydronium gives us hydroxide. 10 to the minus 14, magic number. 14 is a magic number. Simply type this in, take its log, that's our pH. Subtract it from 14, that's our POH. All right, hydroxide, 10 to the minus 14 divided by hydronium gives us 8.1 times 10 to the minus 12. That's that. Our second one, we have hydronium. Just take its log, change its sign, and it's about 2.9. And our third one, we could do this two ways. We could take 14 and subtract 2.9. That's the easy way. Or we could take our hydroxide, take its negative log, and wind up with about 11. Now, when you do the tutorial, and I certainly hope you do, this is exactly what you will see. This is how you must do it to get your 5 points, okay? But there's going to be an online quiz one of these days on Blackboard. And sadly, Blackboard won't let you do this. Not my fault. Blackboard won't let you do this. Therefore, I had to come up with a different strategy. So when you take your quiz, it's going to look a little different. You'll actually be given all 4 values. And you'll be asked which one is wrong. Same problem. It's just which one is wrong. Now this is actually simple. If you look at pH and POH, they must add up to what? 14. If they don't, one of these guys is wrong. That's it. If you type in 3 times 10 to the minus 11 and take its log, it should equal 10.5. If it doesn't, it's wrong. Same thing with OH, type this in, hit its log, it should be 3.5. So the way you would do this, step 1, is this equal to 14? 10.5, 3.5, yep, that's 14. So that means that either this or this is incorrect. All right. Step 2, if we get our sum this correct, convert these into hydronium and hydroxide and determine the correct value. So our pH, 10.51. 10 to the minus 10.51 is 3.1 times 10 to the minus 11. That's right. 3.49 is actually 3.2, which is not this. And so this guy is incorrect. On Blackboard, you would take it, you would type in the correct value, and we would all be happy. Now that's coming up in a while, but again, it's a slightly different exercise than this tutorial, but that's the problem with Blackboard and not me. Any question? All right, here's another question that I always put on a final exam. Always. Maybe I'll change the number just a little bit, but it's always the same question. We have cheap red wine. Okay, I'm familiar with that. And it has a pH of 2.85. What is the hydronium, the hydroxide, and the POH? Always on the final exam. Sometimes the wine isn't quite as bad as this, but pretty much always on the exam. So how do we do this? Well, the easiest one to do is POH, isn't it? We can also take our pH and calculate hydronium. To do hydronium, all you have to do is 10 to the minus pH. So you take your magic calculator, type in minus 2.85, hit 10 to the x, and with any luck, you would get about 1.4 times 10 to the third. This is the equivalent of red wine vinegar. Not something you want to drink, even on a dare. Now, if we know our pH, and we know that pH and POH is always 14, what do? We subtract. You don't even need a fancy calculator to do that. You can even do it in your head. 14 minus 2.85. Yep, about 11.15. And finally, to get hydroxide, what do? Well, we know hydronium. We also know POH, so we could do this two ways. The way that I chose here was to take hydroxide, 10 to the minus POH, that's this thing. So you want to type in minus 11.15 and hit 10 to the x. Again, when you do, you should get about 7 times 10 to the minus 12. Any questions? Now, I'll be really honest with you. The concept of pH is something that is really difficult to teach to general chemistry. This is chemistry and society. So, on your exam, you're not going to have big time calculations regarding this. You're not. This is a concept that when you hit general chemistry is complicated. Most people find it overwhelming. The questions on the exam will be the nature of acidity and basicity. Remember, pH plus POH is 14. Remember 10 to the minus 14. Remember that neutral is pH 7. Acidic is below that. Basic is above that. That's where we're going with this chapter. Any questions? Anyone remember Cabbage Patch?
Yes.
All right. Have a good evening. And I will see you next Monday.